Okay, so let's start on module 3 and first lecture about it. And I just wanted to discuss more into modulations this time. In the past, we have seen mostly the effect of a number of topologies and their performance and analysis. And now just want to go through couple of some concepts in power electronics, I will say. Basic concept in power electronics in this module 3. What we should know, the fundamental or the some background knowledge. We require Snubbers also in power electronics and modulation techniques also. And we know what is modulation. Modulation is basically a technique to turn the switch on and off. Right, that is modulation. Because in power electronics, the components we have like inductors, capacitors, right, transformers, diodes, and the switch. So once a power electronics product is developed, right, and then the objective is always to regulate the output voltage, fix and control the power flow. Say 1 kilowatt, 100 watt, 500 watt, right? So how to do? Only controllable element inside the power electronics is only the switch. Right? These are not controllable element. These are just sitting and based on the input voltage they perform. Right? Based on the input voltage they start performing. And further, to chop the voltage or to control the power flow and voltage regulation with the in small signal analysis we have seen small signal analysis and closed loop control design, that if there is a perturbation in input or if there is a perturbation in load, right, so this output voltage changes, okay, power changes, so how to regulate those, how to control those. Only thing is that through small signal analysis and closed loop control we have to generate the PWM signal for the switch. Okay, so that PWM pattern, this is pulse modulation, right? This PWM pattern is called modulation, turning the switch on and off. So that is another topic of research. And so and this is important in power electronics because there are different ways to turn the switch on and off for a single topology even. Okay, for a single topology even there are multiple ways to do that. And there are researchers throughout their life they didn't work on topologies, they worked on modulation techniques only, different modulation techniques. Okay, so this is modulation, developing the PWM pattern for the switches inside, because that is the only controllable element to achieve the two objectives: output voltage regulation and power flow control. Okay, the rest of the elements they will perform based on the voltage appearing across them. Okay, similarly, snubbers are usually required to limit the over voltage or over current. Okay, so mostly we try to control, we try to limit the voltage spikes, the voltage overshoots. Okay, voltage spike, voltage overshoot to limit the output power. Okay, so let us see some of the effect of using different modulation techniques. Okay, so we have seen high frequency switch mode power supplies. in order to achieve the compact, lightweight, and low cost system, right? We go for high frequency due to compact, lightweight, and low cost system. Okay, so once we move for high frequency, then there are different possibilities. At low frequency, 50 hertz frequency, only one possibility. Okay, so this is just a full bridge converter. So this is input, full bridge inverter, and then this is output. Sorry, this is the full bridge system. It's like this, full bridge. Okay? That's what is here. This is input. Okay, and this is 4 switches, and then this is the output. V naught. Okay, now let us see what is the effect of if we use different modulation, how the same circuit can perform differently. Okay, so first thing is bipolar switching, bipolar modulation. Okay, so we are just turning these switches on and off, the 4 switches, by through some modulation. Okay, and this modulation we are generating again through the carrier waveform or the reference waveform. Okay, so this is a inverter part. We are generating sinusoidal waveform at the output. So this is DC to AC. Okay, so you can see this sine waveform is a reference waveform, which is known as control waveform also. Okay, and this is high. So this is reference waveform of low frequency, say 50 hertz. Okay, that you want to develop output of inverter. Okay, that you want to develop output of the inverter. And basically this is known as carrier waveform, which is high frequency. Okay, so frequency of this carrier waveform is basically switching frequency of the device. Okay, it's given here Fs. Okay, so if it is 100 kilohertz, if you want to control the device at 100 kilohertz, then frequency of this carrier waveform, triangular waveform, is 100 kilohertz. Okay. If you want to do it 10 kilohertz, then this is 10 kilohertz. Okay, it's like that. Okay, so how to generate the gating signal here? You can see that whenever the here the reference or the control is higher than the triangle or carrier, whenever the reference is higher than the carrier, then we basically turn on this switches TA plus and TB minus. Okay, then TA plus and TB minus, they are on. Whenever we control or the reference is higher than triangle, then this diagonal pair is on. Otherwise, okay, otherwise means when the control is less than triangle, which is this one, under the triangle. Okay, otherwise TA minus and TB plus on. Okay, so both are doing a high frequency switching and complementarily. You can say here complementary switching. Okay, either this pair on, if not, then this pair on. It's clear like that. Means they are coupled. Okay, so you can see when TA plus and TB minus is on, when TA plus TB minus is on, what is output voltage? Output voltage is this V naught plus appears here, and then VD and VD minus appears here. Okay, which is plus VD, which is this. And when this pair is on, complementary, when this pair is off, then other pair is on. So this plus comes here, and this minus from here, minus goes there, and you get basically minus VT. Okay, so whenever TA plus and TB minus is on, then you get sorry, so you get basically V naught is VT, and whenever TA minus and TB plus is on, then basically you get minus VD. Okay, so you are generating basically bipolar waveform. Okay, you are generating bipolar waveform, plus minus plus minus plus minus. Okay, although your target is to develop this unipolar waveform at a time, either all positive or all negative. Okay, but you are generating positive negative bipolar waveform like this. Okay, although your reference is this all positive, but you are generating bipolar, positive and negative both. Okay, so that average is this. Now, if we do the fast Fourier transform of this waveform, bipolar waveform, so switching is at high frequency, okay, like 20K, 30K, like that. So if we do the fast Fourier transform, then since it is a high frequency switching and linear modulation, okay, so you can see that here is your fundamental component, 50 Hertz component, which is this. Okay, and then you don't have low frequency harmonics at all. You can see like 100 Hertz, 150 Hertz, low frequency harmonics or second order, third order. You don't have those. Okay, directly you are moving towards switching frequency harmony. Okay, this is basically FS. Okay, this is basically FS. Okay, so to know the spectrum, because in case of DC only concern is ripple, but in case of AC, the harmonic component, harmonic orders are also of concern. Right. So here you can see that harmonic components are given here. Okay. So in this, what happens in this harmonic, that whenever J is odd, then whenever J is odd, then K is even. Okay. And whenever J is even, then K is odd. Okay, so suppose J is odd, suppose J is 1. So 1 into MF is MF. What is MF actually? MF is switching frequency divided by the reference frequency, which is, say, for example, suppose switching frequency or the triangle frequency, carrier waveform. Okay, say it is 50 kilohertz and the reference, your sine waveform you want is 50, then this is 1000. It's like that. So MF means order, this is fundamental, and what is MF? MF is 1000. But if we write this is in terms of harmonic order 1000. But when we write in frequency, then this is 50 hertz and this is 50 kilohertz. Right. Okay. So we want to develop, we want to calculate the order of harmonic, that which kind of harmonic orders will be present here so that you can design filter. So this order. Okay. So you can see it is in terms of MF, like 1000 something, then multiply by 50, so that it will come in the form of 50 kilohertz or something like that. Okay, in terms of frequency instead of order. So MF is 1, then K is even, then it is plus minus 2. Means you have MF plus 2 and MF minus 2. That's what you can see. MF component, MF plus 2, MF minus 2. MF plus 1, MF minus 1 is absent. Okay. And when J is even means, so it is 2 MF and K is odd. We say plus minus 1. So you can say this is 2 MF, this is 2 MF plus 1, this is 2 MF minus 1. This will be 2 MF plus 3, and here it will be 2 MF minus 3. Similarly here it will be MF plus 4, and here it will be MF minus 4, plus minus 2, plus minus 4, like this. Okay, so these harmonics will be present. Okay, but the highest magnitude will be of MF, because MF belongs to your switching frequency. Okay, so what you can notice from here is that with bipolar switching, after fundamental component, you have basically switching frequency component, Fs. Okay, and one thing you see here is that all are doing high frequency switching, and bipolar waveform is appearing rather than unipolar, and that is reducing the average voltage, right? That is reducing the average voltage, because you see what is the what is the average over a high frequency cycle is area under the curve. This positive minus negative is the basically average value. Okay, positive minus negative is the average value. So this is one way, and this is very simple to implement, because you know how to implement is just a triangle waveform is compared with a sine waveform, right? You just need these three. You need here a reference waveform, and you need here a triangle waveform, right? Yeah. So whenever reference is higher than triangle, this is comparator. When reference is higher than triangle, it's high, and whenever it becomes low, it becomes low. So this signal goes to TA plus and TB minus, and its complementary signal goes to TA minus and TB plus. Okay, it is very simple to implement. And comparator, it is just analog system. When it comes to digital programming, FPGA and DSP, it is quite easy. Right? Suppose this you have stored the lookup table, for example, is something. Okay, is something, for example, V1, and this you also stored in a lookup table as V2. So just program that if if V1 is greater than V2, okay, then we can say PWM is high. PWM is high. Okay, else PWM is low. And this is the programming needed. That's it. In DSP FPGA. So it is very easy to implement. Okay. And in addition to the fundamental one, switching frequency harmonics are there. Okay. And all are doing high frequency switching. Either this pair is on or this pair is on. Okay. So this is the fast Fourier transform of this to design the filter. And these are the harmonic components that you know. mf plus 2, mf plus 4, mf minus 2, mf minus 4, 2mf, 2mf, 2mf plus 1, 2mf minus 1. Okay, like this. And the highest value goes to mf, switching frequency. Okay, now same circuitry. Okay, same circuitry, but say unipolar switching. So basically the switches are operating independently. Here you can see earlier they were operating complementarily, right? I had written either TA plus TB minus on, or after that TA minus TB plus is on. It means TA plus and TA plus and TA minus were operating complementarily, TB plus and TB minus operating complementarily. TB minus is attached with TA plus, TA minus is attached with TB plus. But here there is no attachment like this. They operate independently. Yes. Okay, so first thing is what, that one leg is basically you can say high frequency switching, and other leg is doing basically low frequency switching, we can say that way. Okay, so let us say that when so there are two references now, huh? There are two references. Okay, there are two references. So you can see there is like triangle waveform is same as before. You can see starting negative, positive, and all, and this one positive reference, and now we have 180 degree shifted, 180 degree shifted or opposite phase. Okay, this is 180. This is 180 degree shifted or opposite phase. Okay, so now reference 1 and reference 2. This is 1 and say this is 2, and they are compared with a common triangle, same as before, but we have two references now. Okay, we have two references now. So reference 1, okay, reference 1 is say for TA plus like before, and say reference 2 is for TB plus. Okay. Okay. So when the switch is on, when the TA plus is on, you can see this voltage V naught appears here. Sorry, let me see. If this one goes here and then this is off, then this one goes there. 0. TA plus. TA plus is on, then we get plus VD, and this is N, VAN, and otherwise VBN. Otherwise this is on. Okay. Otherwise TB plus is on. If TA plus is on, this is not. Otherwise, if TB plus is on, then it is negative. Okay, there are two ways to understand that. Okay, there are two ways to understand that in unipolar switching. Okay, one thing is that forget about this. Okay, and what we do is that during sinusoidal, sorry, you want this is your reference waveform, okay, that you want to generate at the inverter output that we discussed before also. Okay, so during positive half cycle, okay, during positive half cycle and during negative half cycle, what we can do is that say during so this is TB minus, and say this is TB plus. So what we can do that this lag we can operate at low frequency, say for example 50 hertz, okay, and this lag is operating at high frequency, which is say 50 kilohertz that we discussed. Okay, so during positive half cycle this switch is always on, okay, and during negative half cycle TB plus is always on, okay, during negative half cycle. So this is very easy to do, like this this is compared with a comparator, and this is ground, which is 0. When it is higher than 0 it is high, and it's complementary. When it is lower than 0 it is 0, and its complementary will be opposite. Just getting the getting symbol for this. Okay, so now actually only one reference will be sufficient. Only one reference will be sufficient. Just follow the first reference like before. Okay, like this first reference. Okay, so whenever the reference is higher than triangle, same thing. Okay, and you generate the getting signal for TA plus. You generate the getting signal for TA plus whenever the reference is high. So what happens? The voltage comes through TA plus and then through TB minus, which is VD, right? Which is VD. And whenever it is lower VD, then what happens? Whenever it is lower, then the switch is off. And what happens when the switch is off? This current, which was flowing this way, now this current, because it is inductor current, okay, this current will still flow through this way, but through this diode now, like this. Okay, it will flow through like this. Which means what is the output what is the voltage now? Earlier voltage was VD, but now the voltage is 0, short circuit, switch and diode, and it is short circuit. So current was in this direction, it is still in this direction, but now it is 0, which is this. Then again switch is on, then again it is plus VD, and when the switch is off, again the diode and the switch conducts, like, because this is always on for up to here half cycle, and then again it is 0. Okay, so what is happening? TA plus TB minus is on, and then basically DA minus and TB minus is always on, right? That's what is happening. Okay, so during earlier this was also high frequency and this was also high frequency. They were on together, they were off together, they were coupled, but now they are independent. Okay, and when it comes to negative cycle, then TB plus is on. Okay, TB plus is on, and now basically, oh sorry, now this is high frequency, right? So this going this way. Yes. Okay, now basically TA minus is doing high frequency switching now. Okay, so whenever, and TA plus is completely off. Okay, TA plus is completely off in second half. Okay, earlier they were doing complementary, but now there is nothing complementary. Okay, now TB plus is always on, which is this, right? TB plus is always on in negative half cycle. Okay, so like this. So this is always on. Okay, and this lower one is doing high frequency switching. So when this is on, when TV plus is on, okay, so this plus is appearing at the negative terminal. When it goes back, when TA minus is on, okay, when TA minus is on, which is negative voltage. Earlier we were turning TA plus on and TB minus was on, so it was giving you positive. But now after half cycle, we reverse the sequence. TB plus is always on and TA minus is doing the high frequency switching. So current which was flowing through this way, now it is flowing through this way. So that it is negative, it is positive, and then it is returning through this which is negative. Okay, so now here TB plus is on and TA minus is on during positive. Okay, and when TA minus is off, because it is high frequency switching, so when it is lower than the control, then when TA minus is off, then what happens? This current which was flowing through this way and returning through TA plus, short circuit. When it is, whenever it is 0, it means it is TB plus and TA minus, TA plus, both DA plus, causing the zero voltage. It is circulating current, zero state, introducing zero state. Okay, so here you can see one leg is doing high frequency switching unipolar, one leg is doing low frequency switching, okay, which is 50 hertz like this. Okay, and there is no complementary switching now. TA plus TB minus pair is conducting, TB minus is low frequency switching. Similarly, TB plus TA minus is conducting, TB plus is basically low frequency switching. Okay, and you can see that instead of going positive and negative, it is positive and zero, because you are allowing a diode conduction because of continuous switching. Earlier you immediately change the switching, right? Earlier either this is on and you turn this switches off immediately and you turn this pair on. Right now we are not doing it, we are doing this pair continuously on, so that this current still flows and then find the alternative path, causing a short circuit, causing a zero voltage instead of going it negative. So you can see that when there is a positive half cycle of the triangle, okay, the output voltage magnitudes are always positive, positive and zero, and when it is negative half cycle, output voltage magnitudes are always negative. So it is called unipolar switching. Okay, and you can see compared to this positive negative, this is more sinusoidal, positive increasing and then negative. This is more sinusoidal. So circuit remains the same, only thing is that the modulation technique is different. Okay. So now if we do the fast Fourier transform of this, okay, you can see there is nothing at MF. There is nothing at MF. Okay, you have it at 2 MF, twice the switching frequency, the harmonics. But you don't have at 2 MF also. You can see this is 2 MF, which is ground. Okay, only you see is 2 MF plus 1 and 2 MF minus 1. Okay, so you can see that the topology is the same, right? Topology is same, and just basically a switching scheme is different and very minorly different. Okay, but you can see their output and harmonic performance is different. Okay, one thing is that in bipolar switching you have MF, and here in unipolar switching you have 2 MF. So here if we see, okay, if we see in terms of harmonics, so here you can see it is more and here it is less, right? So because of that you can see if the filter requirement, okay, so here filter requirement is less compared to unipolar. In bipolar it is high because you have to remove low frequency, I mean half of the frequency, that one, instead of MF here it is 2 MF. Okay, yeah, and when we see in terms of losses, so you can see Here two switches are doing high frequency and two switches are doing low frequency. But here all four switches are doing high frequency. Okay, so here you can see switching losses are high. Here you see switching losses are high. Okay, and here you can see switching losses are low. Okay, so that affects basically efficiency and heat sink size. Efficiency and heat sink requirement. Okay, so just you can see that a minor change in the minor change in the switching scheme or modulation scheme, how it can affect the performance. It can require, I mean, minor change in modulation means just minor change in the coding. Okay, no, nothing in hardware, minor change in coding. Okay, so that can reduce your filter requirement, your heat sink requirement, and improve your efficiency also. Okay, so this is the effect of modulation. I mean, circuit remains the same, but a different modulation scheme can result into different performance of the power electronic circuitry, because power modulation is the key to control the switch. Okay, and that can result into different performance. Okay, now let us see the Snubbers requirement. Okay, so in power electronics, right now we were just talking about filter. Filtering is very important. So this is a DC to DC converter. Okay, and we can see that this is capacitive output filter. Okay, and now you can see this is inductive output filter. Okay, so the performance is different. Like if it is a capacitive output filter, you can see output voltage is fixed, right? And here it is your input DC voltage. Okay, and here is your transformer inductance. Okay. So following this formula, L di by dt equals to delta V. So whenever the voltage difference appears between them due to the switching, okay, di by dt will rise. So whenever a positive voltage, it's rise, and whenever negative voltage, it falls. Okay, giving basically peak currents. That's what it is saying, peak current, which will be higher with higher voltage difference. If delta V is high, then delta I is high. Then delta I is high. And when it comes to inductor, so it is inductive output filter, so current is fixed. Say I naught. So what is the current at this side? N I naught. Right? Turns ratio. Sorry, it is NT, so it will be I naught divided by NT. So simple. Okay. So here is lower peak current. Here it is say this current. And what will be the current here? Current here will be this. I naught by T, or say I naught dash minus I naught dash. Okay, current limiting. And here it is basically two voltage sources, this one, and based on the switching, the voltage difference appears and current rise and current fall like a triangle waveform. And so this peak current is 2 times, because in triangle the area under the curve is half of the full one, right? Okay. And here it is basically already square wave. But here if you have a triangle wave, then this area is half. So this peak should be double for the same power or the same current. Okay. And capacity filter. So different filter will give basically different waveform, and the analysis is different. Okay. So it's like this. You can see this is capacitive filter. The peak current for the same power you can see 100. Okay. And this is inductive filter. You can see it is approximately 50, 50, 52, 40, 60, 50, 52. So that's what I was saying. In capacitive filter, the peak current is double, because it is a 2 voltage sources and then inductor. So current just rise or fall. Okay, but here because of output inductive filter it's flat, and the other side it will reflect I naught by dash. So you can see this is I naught by dash and minus I naught by dash, I naught by n and minus I naught by n. It's like that. Okay, this is inductive filter. Okay, but in inductive filter this is a major problem uh, due to cycle loss and ringing. So what I was saying that this is the when there is an output inductor. So this is the output current basically, output current. But when it comes to input, I was saying that this is square waveform, right? But this cannot be a square waveform as it is because you have inductor, transformer leakage inductor. Okay. So the change in the current cannot be instantaneous because you know this is inductor's property to avoid the change in current. So based on this leakage, which is L di by dt, right? Based on the value of the inductance, it is high or low. Okay, if it was n I naught, for example, I naught, so when it changes to opposite direction, it will take time. Okay, then it is I naught, and then again it will take time. Okay, then I naught, then again it will take time. Okay, so this slope will depend upon the value of inductor. If inductor is high, then this will take longer time. If this leakage inductance is 0, then this is square. But 0 is not possible. And if it is lower, then it will be faster. Like this. Like this. Okay. So what happens that it takes time. That's what is happening. You know, it is taking time to change. Okay. And during this time, what happens? During this time, what happens that whenever inductor is changing the direction, during that time what happens that there is a difference between this and there is a difference between this. Earlier this current was flowing through this and coming, so that L current through the inductor multiplied by the turns ratio is I naught and perfect. But now this is going down, so this multiplied by turns ratio is not this anymore, this is flat, but this has gone down, right? It is changing, it is going down, so this multiplied by turns ratio is not this. Okay, so this current multiplied by the turns ratio is basically less than I naught, because this is same as I naught, but this is less than I naught. Okay, so where this difference will go? Okay, that difference. So earlier this one was flowing through this and then this diode and then coming back. So now this so still the same thing is happening. This NL current through the inductor multiplied by the turns ratio will flow through this and come back. But the difference will flow through this pair now, because there is no other path. There is no other path. So difference will flow through this diode pair on. It means all the 4 diodes are on, causing a short circuit across the transformer secondary. So whenever the transformer inductor is changing the direction, okay, there is an imbalance of the current between output and input because of inductive output filter. And the balance of, and because of the imbalance, this difference will flow through the other pair of diode, causing a short circuit across the transformer. That's what you can see, that all 4 diodes are on. This is say D1 D4 and this is D2 D3. It is decreasing and the other side it is increasing, right? Like this, one pair decreasing, diode pair, another diode pair is current is increasing. All the diodes are on, causing a short circuit across the secondary. Causing a short circuit across the secondary. It means secondary voltage is 0 or the power transfer is 0, because voltage into current 0 into something is 0. Okay. Yeah. So this is called duty cycle loss. That instead of transferring power for the entire cycle, which is say 50% positive, 50% negative, now you can see it is 45 and this is 45. This 5%, 5% lost because of this. So this is called duty cycle loss. Some duty cycle loss is there. Okay. And if inductor is high, this time will be larger, then duty cycle loss will be larger. Okay. And then in order to get the output voltage, same output voltage, because you are shorting the secondary for some time, so your output voltage is reduced. It is, say, V in multiplied by N. So it is NV in and then 0. Then NV in and then 0. Okay. So this 0 period, if it is increasing, then your output voltage is decreasing. Then you have to increase the turns ratio somehow to get the same output voltage. So somehow if duty cycle is larger, then you have to increase the transformer turns ratio to compensate for duty cycle loss and to get the same output voltage. Okay. So this is one problem if we use a different filtering. And what happens that during this time when the diode is when the all the four diodes are conducting, whenever the transformer is changing the direction, okay, all these diodes, they have picofarad of capacitance. Okay, then you can see that during this transition, okay, during this transition, this inductor, transformer decay inductor, and the this diode capacitances, they resonate like picofarad, and this diode is basically this inductor is microhenry. Okay, they resonate basically and causing this voltage stress, voltage ringing, and this peak of the voltage ringing is basically 2 times of this NV in. This voltage will get right. 2 times of NV in. Okay, so you need basically higher voltage rating diodes because of that, because of inductive filter. Okay, so that's what is happening. You see, they have picofarad of capacitance in inductive output filter. Okay, so we can see, you can see the secondary side ringing is happening, causing almost 800, 700, 600 plus, or yes, 200, 400, 600, very close to 800. Okay. And you can see that this diode is conducting. Similarly, another diode pair will be conducting, causing duty cycle loss. Okay, so to avoid this, then they use Snubbers circuitry in inductive output filter. So capacitive filter has basically higher peak current, and inductive output filter has basically reduced peak current, half of that. But you can see this number requirement is there. So after this number, you can see instead of 800, now it is claimed to 400. And you can see duty cycle loss, which was also here, duty cycle loss. During this time, duty cycle loss. During this time, duty cycle loss. Okay. So which is still there. Okay, whenever the diode is changing, whenever the transformer is changing the direction, it is still there. But you can see after Snubber, the 800 volt has been claimed at 400 volt, so that the switching requirement can go down. Okay. But you can see this solution is lossy solution. Lossy solution means all the four diodes are conducting, they are causing losses instead of two diodes conducting before. Okay, and now this RC snubber, so this resistance, okay, the power, the energy is circulating through that, the resonant energy. Okay, so that is dissipated in these resistances. So very easily 2 to 3% efficiency loss happens very easily. Okay. Yeah, but you see the snubber effect, how it was before, how it is now. Okay. Okay, but anyway, as I said, this is not effective solution because of four snubber requirement, and the resonant energy will flow through those those resistances causing the energy to dissipate, which is a loss basically, 2 to 3% loss. Okay, so a better solution is active clamping, which is this. So there is a switch here. So what happens that whenever the switching happens for the change of the direction of current, and you have duty cycle loss, and you have this rectified diode ringing from this time to this time, right? This ringing, if you see, is for a time when the diode is changing direction, it starts, right? So what happens that during that time we turn the switch. During that time you turn the switch on, and the current which was flowing through this now flows through this. So it is short circuit, and whatever this pre-charged capacitor voltage will appear across them like a capacitive output filter. Okay. So the difference delta I, what I said before, that this Ni naught, sorry, this NILK was not matching with I naught. So this Ni N and Ik is flowing through this, but the difference was flowing through the other pair of the diode. Right? Now basically that basically flows through the switch. Instead of flowing through the other pair of diode, it flows through the switch. Okay, and the diodes are not able to see the inductor. Diode will see this short circuit and this capacitor. Okay, so diode voltage. So earlier only this pair was conducting. So what is the diode voltage when this diode is conducting? What is this diode voltage? This diode voltage is this capacitor voltage. Okay, so earlier the diode was conducting, and then it is claimed at this capacitor voltage. Okay, and then when this is over, and when the current has gone down basically to this value again, then the switch is off, because again then after that this pair is conducting, current is flowing through this other diode pair. So when the power is taken from this diode pair to this diode pair, or from positive to negative, during that time the clamping switch is on, this difference flows through this, and this is short circuit. Voltage across the diode is basically capacitor voltage, and then that's it. Clamping happens by this. So you don't need 4 RCA or RCD Snubbers at all, which is causing losses. Only the loss in one switch, for as well as the difference flows through the two diodes. So two diode losses versus one switch loss, even the difference. Okay, so this is better still. Okay, so this was found efficient solution. So that was the topic also of the lecture, that sorry, clamping. Okay, so instead of using RC RCD, you can see just a clamping switch can do the job. So whenever there is a difference on current, this flows through the switch, and the voltage across the diode is clamped at the capacitor voltage. Okay, very simply, directly, immediately, so that there is no ringing, and then there is no issue of requirement of additional snubbers due to resonance. The voltage rating goes 2 times. Okay. So this is active clamping in voltage fed converter. Similarly, once I had taken a lecture on current fed, and we had seen it that in current fed also. So here it is a problem of turn off, diode turn off. Okay, here it is the switch turn off basically. Okay, that whenever, like, since the flat current is flowing, continuous current. Okay, so you should always provide a path for this current to flow. You cannot interrupt the path, otherwise where the current will go. Okay, so earlier if the current was going through the switch, okay, and you turn the switch off, then this current cannot flow through the transformer immediately, because same reason we said, it takes time to rise, take time to fall. But for the instant, this current immediately flows through the capacitor, because it cannot flow through the diode, cathode to anode. And this capacitor is very small, nanofarad, right? So just the voltage rises very fast, because this entire input current, 10 ampere, 100 ampere, will charge this capacitor. Okay, and the switch will damage. So in the past, several circuits, several similar circuits were given, but active clamping was considered again as the optimal solution, because whenever you are changing the switching, okay, the inductor will not respond the current change instantly, so it will do it slowly. But during this time, what happens, that this switch is on and this inductor current can immediately flow through this capacitor. Okay, and capacitor voltage is the switch voltage is claimed at capacitor. This is 0 plus Vc is switch voltage. Okay, yeah. So earlier the voltage was rising, and you same thing, you will again need RC or RCD snubber. Okay, but here you turn the switch on, this current flows this way, bypass like a boost converter, and this circuit is saved basically, and voltage across the switch is basically the capacitor voltage by Kirchhoff voltage law. Okay. Same thing here in a half bridge one. Okay, the switch was on, and when the switch is off, the current immediately will flow through the capacitor, right? But now it will flow through this circularly. Okay, saving the switch. Okay, similarly for this switch, when this current was flowing through this switch, when this is off, this will flow through this capacitor, causing overshoot, but now it will flow through this. Okay, so active clamping circuitry act as a snubber to clamp the voltage to overcome this resonance for the commutation of the diodes or the switches efficiently compared to RC or RCD snubbers. Okay. So in converter with inductive output filter, this is quite important. Okay, converter with inductive output filter, it is quite important. Similarly, converter with input inductive filter also, it is quite important. But when it is capacitive both sides, right? When it is capacitive both sides, then there is no problem like this. Only the problem is high peak current 2 times. But whenever there is an inductor, either output or input, then you need snubbers. And active clamping is a efficient solution compared to the RC or RCD lossless snubbers. Okay. Now, just again coming back. So earlier we discussed the modulation of inverter. Now this is just about a full bridge converter, a modulation in full bridge converter. Okay. That full bridge DC to DC converter, we always talk about source switching part because of high frequency switching, and this switching is quite high, 100K or something. Okay. Okay. So somehow different modulation can give you basically different performance or source switching range. Okay, so one thing is basically one modulation is say duty cycle modulation, means this pair S1 S4 on together with duty cycle changing 0 to 0.5, and then S2 S3 on together with duty cycle changing 0 to 0.5. It is varying. This is on and this is on. So basically at full load, okay, at full load or rated load, okay, duty cycle is at 0.5. Then say if you are at half load, say it is 0.3. Say you are at 20% load, say this is 0.25 or something. Say this is 0.35, say this is 0.25. It means their pulse width modulation, pulse width is changing. Say this is 50, and then again after 50, or it is say 35, or say this is 20, like this. The duty cycle is changed. Okay. So if this duty cycle changes, then what happens? That the purpose of changing the duty cycle is to regulate the output voltage and regulate the control the power flow. Regulate output voltage and control the power flow. Okay. So now to regulate the output voltage when the load changes or to control the power flow, you have to block or unblock the circuitry for some time, for longer time, and then blocking unblocking is done basically by the switching. That okay, I will unblock for 100%, say this is 50% and this is 50%, 100% unblocking, which is rated load. Now say I will do unblocking for 70, so I will do unblocking for 70%, 30% I will unblock, 30% I will block, and say it is 50% load, something like that. Then I will do blocking basically for 50% and blocking 50% and say 20% load. Okay. So what happens that as the duty cycle, so when the duty cycle is high, which is high as 50%, the leakage inductance is able to store energy at the highest value. Okay, because during this time, the entire current flows through this, which is I in, and inductor stores energy, which is the full current. For example, 100 ampere. So energy stored here is basically L half Li square, 100 square. Right? Energy stored here is half 100 Li square. Okay. And when you want to do the soft switching turn on and turn off, okay, suppose this switch is S1, S4 on. Now basically S2 and S3 turn is coming for soft switching. Okay. Then what do we do? When we turn this switch off, S1, and when we turn this switch off, then what is happening? These switches are, so when this switch is on, what is the voltage across the switch S2 or C2 is basically V in. Kirchhoff voltage law, V in plus 0 is V in. Similarly, V in plus 0 is V in. C3 and C2, they are basically charged at V in. So when this switch is off, now they are exchanging energy. They will be charged at V in and they will discharge at 0. And then there is a possibility because of the peak current of the leakage that their body diode conduct. If not, they are discharged to 0 and then the switch can be turned on with 0 voltage switching. Okay, because you discharge their capacitance to 0 first. You discharge their capacitance to 0 first before turning them on. So who is discharging? This inductor is basically charging this and then discharging this. Okay. So this is discharging one capacitor, these two capacitors, and charging these two capacitors. So this energy is stored half Li square. Okay. This should be higher than. If this is higher, then C V square, V in. Okay. If it is higher, then of course diode conduction will also happen. And if it is equal, then after discharge, immediately the switch turn on will happen. Okay, so when this energy is high, then you are assuring GVS all the time. Despite anything, and what happens that input voltage also changes. For example, solar photovoltaic application and say fuel cell application, input voltage also changes. But suppose forget it now, suppose right now it is fixed. So all the time this all the time the energy storage in each capacitor is fixed, which is CV in square despite of the load current. So now suppose the load is 20%. Then earlier 100 ampere was flowing, now this 100 ampere will become 20 ampere. Right? So CV square is the same because whenever the switch is on, the other switch will still store input voltage, will be charged at input voltage. Doesn't matter what the load or what the current is. Okay. So what happens now? Earlier, half L into 100 square was the energy to charge discharge CV in square. But now energy is basically 20 square to charge and discharge this, which is not possible now. Which is not possible now because inductor is not able to store sufficient energy during this short duty cycle. Okay, and the circuit will lose GVS. Circuit will lose GVS because this remains still the same as before with the change in load. Okay, but energy has gone down because of the change in load, and now this is not sufficient basically to charge and discharge the capacitor. Okay, so one argument can be okay, energy is half Li square. Since current has gone down because of the load current has gone, we can increase the inductor. Okay, but don't forget one thing, that if you increase the inductance, then your power rating goes down. Okay, then power rating goes down. That you don't want to reduce. Okay, that you don't want to reduce power rating because power rating is fixed. Say 1 kilowatt means 1 kilowatt. Okay, so to avoid this, then people propose second modulation. Circuit remains the same, and this is phase shift modulation. Means duty cycle is always 50-50%. Okay, it is not a duty cycle modulation like this. Not like this. 50, 30, 20. It's not like this. It is always 50-50. So what happens that S1, S2 is having this modulation, like this getting signal. Sorry, this one is S1, this one is S2. And you can see the other pair, like this one, S3, S4. Okay, they are phase shifted. Earlier S1, S4 were same, and S2, S3 were same. Alright, so you can see S1, S2 were complementary. So S1, S2 is complementary, and S1 and S1, S4 were same, but you can see this is S1 and this is S4. S4 is shifted by 50%, phase shifted, but duty cycle is still 50%. Okay, so fixed duty cycle, which is 50%, but phase shifting, you can see this phase shifting, and this phase shifting will depend upon the load. If load is 50%, then this can be 30% or something like that. Okay, and voltage appears at the output whenever there is an overlap, which is this. Whenever there is an overlap, which is this. So this way still you can maintain the transformer peak current quite high, half Li square. So this I, the average value will go down a bit, okay, but you can see the peak value where the change is happening, that switching turn on and turn off, when the change is happening, that is still you can maintain high. So this Li square is still higher than CV square, and this will offer you higher source switching range. Okay, because you are maintaining the peak current where the switching is happening. Okay, where the switching is happening, and because of that you are able to extend the source switching range compared to the duty cycle modulation by using the fixed duty 50%, but phase shift as the load changes, you do the phase shifting between S1, S2 remains fixed 50-50 and complementary, and you can see earlier S4 was same, but now S4 is phase shifted. Earlier S1, S2 and S3 were same, but S3 is phase shifted with respect to S2. Okay, and you maintain the peak current high, and basically you are able to discharge the capacitors. You are discharge the capacitors of the devices, and you are again able to get the source switching. Okay, so it's like this because of phase shifting. You can see these switches are on. Now this switch is off. Okay, this is still on S4. Okay, so it basically discharges discharges this capacitor and charges this capacitor. Okay, and then diode conduct, and then basically the switch conducts. Sorry, let us see again. Switches were on, now this switch is off. Now this is basically discharging this capacitor. Okay, and this diode conducts. This is very short time. After that this switch is off. After that S4 is off. Then this is charging, this is discharge, this is discharge, this is discharging, and this is charging. Then again its diode conducts, and then both the switch conducts. More number of intervals are coming this time because of phase shifting. But overall is that this peak current is maintained due to the phase shift, constant duty cycle. Okay, and you are still able to discharge the capacitances one by one and get the short switching. Okay, now you can see the phase shifting has changed. If the load is less, now again you are coming to say full load. So you can see that phase difference is changing. This one S1 and this one is S4. The difference is very less, say 5%. So you can see the peak current has increased even. Okay, the shape is changing. So this is phase shift modulation to extend the short switching range. Okay. Another is saturable inductor to extend the short switching further. In addition to the modulation, you can put some, you can utilize some components. Okay. So this saturable inductor. Saturable inductor, what does it do? It has a property, right? Okay, that its inductor value is basically increase with current, and after a particular current it's fixed saturation. Okay, so say for example after 10 ampere, after some current, basically it saturates and it has a fixed value. Oh sorry, it saturate means it's short circuit. Saturate means it is short circuit. Okay, so when the full load current is flowing, then we already know that at full load you don't need any assistance for short switching. So at full load current, the saturable inductor is short circuit, right? And basically current flows like a normal circuitry, and you are getting short switching. Okay, so like it is, we are comparing with this one, half Li square with CV in square. So this is fixed. And earlier I said that this is going down, and because of that this is not able to discharge the current. And I was saying that in case if we can increase the L value, then we can basically, if we can increase the L value, then we can increase the energy again, because this I is going down, increase L, energy can be increased for short switching. But I said if you increase the L value, then power rating will go down. Okay, power rating will go down. So saturable inductor is doing a compromise. At full load or near to full load, it is basically short circuit. So your inductor is still the leakage inductor, and you are able to transfer the rated power, and you are getting the short switching because of this. When you are at light load condition, say less than 35% or less than 50%, then this is the cutoff current for the saturable inductor. Okay, and its inductor value will start coming into picture. So now when this current has gone down 1/3 or below 1/3, then this is half LLK plus saturable inductor value multiplied by I square, and this I is low but this is high now. This is high now at light load current. Below cutoff current its value will come into picture. Okay, so this increased energy has gone up, half L value has gone up, so energy has gone up, and this is again able to charge and discharge your Snubbers, these capacitors. Okay, and you are still able to obtain the source switching at light load condition. Okay. Yes. Another is, like earlier we were talking about the leakage part. Okay. Now let us see the magnetizing part of the transformer. Okay. So magnetizing part of the transformer is always fixed, small value. Whenever the this switch is on, okay, uh, 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 the transformer current increase and then flat, and when the other pair is on, it decrease and then flat. Okay. Earlier we assumed it zero. Okay. But if transformer inductance is very large, we assume it infinite, so its contribution is zero. Because if it is large value, then its impedance is large and in transformer magnetizing current is zero. But if you basically make transformer quite weak, okay, that its current is basically having some value. Right now it is 0.7, it may be 1 ampere, it may be 2 ampere. Okay, and where this current is coming from? It is coming from here, which is coming from leakage. So leakage current is basically transformer current plus output current. Earlier we were saying leakage current is output current. Okay. Now if you reduce the transformer magnetizing, then you are increasing the leakage current, which is this. Okay. And this is able to basically obtain the source switching at light load condition, because at light load condition this magnitude will increase further. Okay. Okay. So modulation techniques we have seen in DC to AC inverters, or say DC to DC converter with duty cycle modulation and phase shift modulation. They can give you the variable performance. Okay, better performance, soft switching extension is possible. And clamping snubbers are more efficient compared to RC and RCD we have seen, because one single switch loss will be there and the capacitor will clamp the voltage for both voltage fed and current fed converters. And short switching extension is possible using the modulation technique when we move from the duty cycle modulation to phase shift modulation, as well as by using some external components, switchable inductor at light load, or the magnetizing inductance by reducing the value of magnetizing inductance so that current from the leakage is increased accordingly, obtaining short switching for the light load conditions. Okay, so utilizing the transformer magnetizing value in addition to leakage. Okay, so there are multiple papers on those. If you see about saturable inductor, you will see there are multiple papers on those magnetizing inductance, utilizing magnetizing inductance for short switching. There are multiple papers on those. Okay. That's it, and we'll be happy to take any further queries now on these fundamentals of modulation and snubbers and short switching extension. Any questions?
Hello, sir.
Mm-hmm.
Hello.
Yes.
Am I audible? Yeah. Okay. I have a doubt regarding that active snubber. You had shown some capacitor charging path. How that capacitor will discharge?
So basically initially it charges and then it discharges to the switch pair.
In the previous one, not the current FRED.
This one, right?
Yeah, yes.
Yeah, it's the same thing. Like I mean, right now it charges. Right now it charges. Sorry. The capacitor is charging. This extra current freewheeling. Oh, the switch direction is different, it seems.
And that capacitor will be in negative, charge will be in the negative position. Then how it is there? That is the question.
Mm-hmm. Yeah, then it is discharged through the diode. I will just use a different slide. Sure. Yeah, yeah. Okay, so initially it charges this way, and then I think when the diode pair is conducting, like suppose this diode pair is conducting, then it will contribute, it will transfer back to the output, like this way. Sorry. When it is negative, then it will sorry. That is negative. Yes. So when it comes to, during the when the transformer is changing the direction, okay, so that time it is circulating, okay, and this is charging and discharging. And when it is coming back to the steady state, for example, that when this diode is conducting, this one and say this one, okay, then so this one means this is the direction, okay. So this will also follow the same. It will contribute back to this, which is discharging now instead of charging, discharging. Okay. Or during negative cycle, when this diode is conducting, okay, which is now, okay, when this one is conducting, then it will basically pass through this. Okay. So initially like this capacitor, but like when the transformer is changing this direction, it will store this energy, and when it is steady state, okay, then it will transfer back through the particular diode pair which is conducting. During negative this one, and during positive, then again it will store energy, and when it is positive, then through this one it is circulated back to the output.
Okay, sir. Okay. Okay.
Excuse me, sir. Good evening, sir. Sir, I have one doubt regarding the phase shifting techniques. Now, like these extended phase shift and triple phase shift, like that, they are there, no, sir. So, what is the main advantage of those compared to this simple single phase shifting, especially
Say
for
again.
current fed converters? Which one is
Say again.
applicable?
Say again a bit loudly.
Sir, like in this phase shifting techniques, we are having like single phase shift and double phase shift and like triple and like extended phase shift and all. So which one is more preferable like, in case of the current bed? How does it mean which is more advantageous to reduce the circulating current loss? Like
Yeah, current fed we didn't discuss the phase shifting part. It was mostly here. I think in voltage fed. Yeah, but you can
yes, sir. In any either voltage fed or current fed, in which techniques like you are having
no, you
this
can apply to both. You can
triple
apply to
phase?
both if you want. You can apply to both also. You can apply to both.
Okay.
You can apply to both. Only thing with phase shifting will be that during so this is active timing, and this is basically non-active timing. So during this time, basically circulating current will cause the loss, which is what is this time is active timing when the switch pair is on, and this time is not the active timing. This time is basically when the switch and diode is conducting like this. Sorry. This one. So this is a kind of loss because it is short circuit. No power flow through the input. Alright. So this part is loss. Okay. So during the designing, we have to take care of this portion that how this circuiting current can be minimized to result into high efficiency. At full load, it doesn't affect because full load duty cycle is 50%, phase shift is 0. At light load, it affects when the phase shift starts increasing.
So is there anything like a backflow power? Is it same as circulating current loss or is it anything different?
No, backflow power is there, and that's why this modulation is still is efficient because if you see for some time the power is flowing back, you can see energy recovery. Power flows back to the source basically. So you are saving energy during this time, as well as you are reducing the switching losses. So somehow overall you can get a similar efficiency compared to the duty cycle modulation. So the energy that was there in the Snubber capacitor is just going back to the source rather than dissipating immediately to the switch by hard switching.
Okay, sir. Thanks.
Mhm.
Hello,
Mhm.
hello.
Yes.
Sir, why we said that bipolar inverter can provide high reactive power in comparison of unipolar?
Reactive power is basically based on your requirement. If you have to provide, see, let us see. Generally, the target is always for unity power factor mode of operation. Okay, but if you see that in bipolar harmonics are higher. Okay, in bipolar harmonics are higher. Okay,
Yes, sir.
yeah. So the harmonics are higher. That affects your if harmonics are higher. Then that affects basically your power factor.
Okay.
Yeah, it affects your power factor. So that is basically the power factors are two: displacement power factor and the basically true power factor. So this affects the power factor. But here harmonics are lower, which basically causes the unity power factor. Okay. So this way we can say that the bipolar is more towards injecting reactive power compared to unipolar.
Okay,
But yeah, but this is not a general statement. Whenever there is a requirement, whenever there, suppose for example, fan kind of load, fan is inductive load. In any case, you need reactive power and you have to supply it. Okay, so that can be done by unipolar also. There is no restriction on this. This can also provide the same reactive power.
sir.
Yeah, because
I read the reason that in bipolar we are changing the voltage from minus VDC to plus VDC, and in unipolar we are changing voltage 0 to VDC.
0 to VDC.
So that's why bipolar can provide uh, a high reactive power in comparison of unipolar. But I did not get the reason why it is so.
No, no. I mean, the purpose of saying is that because of what should I say? That mm, if we see high frequency with respect to the low frequency, you can see it is having a continuous phase difference, right? Positive, negative with respect to all positive. It has a continuous phase difference. Okay, so phase difference means reactive power. So they might be willing to say with that it is able to provide higher reactive power. But reactive power supply, if we see, reactive power supply is based on the load and based on the phase shifting of the current, not the voltage. Right now, what we are saying is basically voltage, right? From negative voltage to positive voltage. Okay, but the
Yes, sir.
reactive power is basically phase difference of the current with the voltage, and that comes basically from the load. Okay, that comes basically from the load, and any kind of switching will able to provide that one, because once load has caused the phase displacement, the current phase displacement will come from the source directly.
And sir, why we said that circulating current also consume reactive power?
Yes, yeah, circulating current mainly consumes reactive power actually, because it is not contributing to the fundamental power, the fundamental power or the real power to the output. Output is not getting, because fundamental power is the useful power, but the circulating current is not providing the power to the output.
Okay, sir, but it means power which will not provide the fundamental power, it will be called reactive power.
No, no, that has two component. That is basically a loss component, and that is basically a reactive. The reactive component is coming due to the presence of inductance in the circulating current, right? If you see, let us see. See, this is circulating current, है ना? Just a second. This is circulating current, okay, which is basically the inductive component is causing the reactive power, the drawing the reactive power, and the loss that is happening is causing basically the active power, real active power. So if
Means due to the inductance, we are calling it is reactive power.
reactive power, because of the inductance, when we see the voltage and current, let me see if I have it. Here you can see this is the transformer voltage, input voltage, okay, and this is, you can see the current, transformer current due to leakage inductance, and you can see this phase lag is coming due to the leakage inductance, which is pulling the reactive power.
Okay, I got it.
And the same is present during circulation also, but that has two components, one is loss and one is reactive.
Any further questions?
Sir, one question, sir.
Mhm.
Sir, in case of full bridge and phase shifted full bridge, the issue of flex walking may be there, no?
Issue
Some
of
flex walking, the DC component comes into the residual.
no. Generally, as long as the switching does not have the different pulse width, then it will not come.
But gradual accumulation of flux shall be there, no, sir?
Let us see. So say when the positive voltage is applied, right here, positive voltage is applied across the transformer V in, flux will start rising, right?
Okay. Okay.
Yeah, flux will start rising, and after that you can see it is 0. Okay, then flux is constant. Okay,
Okay.
flux is constant, so it remains constant further, and now it is, you can see, negative voltage has come now due to diode conduction, and then due to the other pair of switching. Okay, then the flux starts going down after that.
I have seen some papers in which a DC capacitor is put in series with the winding and
Yeah, many people put here as basically blocking capacitor.
Okay.
Yeah. But they put basically just for a safety reason, that in case there is a mismatch in their switching of S1, S4, and then switching of S2, S3. If there is a mismatch in the switching, then a DC component will appear. There is a mismatch in the pulse width basically of this, then it will appear. Then they put in advance also the blocking capacitor CB to avoid this. Okay, but
Okay.
as long as you're switch, so basically what can you do, that we can basically put a ammeter here, and we can see, and you can put that probe, probe basically at DC value. So if, as long as it is in millivolt or something, then it's a 0 basically. Okay, as
Okay.
long as millivolt, it is 0. Yeah. So if you see that this voltage is quite a bit higher, for example 5 volt, 4 5 volt, then you can consider putting a blocking capacitor. That is due to, that is not due to phase shift, it is due to basically mismatching of your switching.
Okay, sir.
Yeah, and if it doesn't come, if it is in millivolt, then you don't need a blocking capacitor, your switching is perfect, then there is no flux imbalance issues at all.
Okay, sir. So this is saturable inductor. No? What are the criteria to be considered when selecting this one?
Just main thing is that two things. One is basically the resistance of the saturable in core basically, because it will cause the loss in that. And another thing is basically cooling, because what happens that at full load or near the full load, the saturable inductor core, since it is saturated and current is passing, it will be heated. It will become hot. It will be heated, because at light load condition it is acting as an inductor. At full load condition it is acting like a short circuit. So the inductor will become hot, saturable. Yeah. So
Oh,
cooling is the concern that time. You have to cool it. Okay. And its resistance should be lower, so that at full load it should not reduce your efficiency.
okay, sir. Thank you.
Mhm.
Do we have any more questions?
Hello, good evening, sir.
Mhm.
Sir, if you are using gallium nitride in place of silicon, so will it improve the soft switching condition in light load?
Like short switching condition, in the sense, if we think of short switching, then possibility in the sense that gallium nitride, they have basically low capacitances. So when we were talking about this half CV square, right, that Li square, half Li square should basically discharge the half CV square, V is V in, but if C is very low, then this energy is low basically. So this will extend your short switching range, because energy stored by them is quite low. Okay, so that will extend your natural source switching range by itself. Okay, in other words, we can also say that even if your converter enters into hard switching region, okay, the energy storage is quite low. That the losses due to hard switching is less compared to the silicon devices. So when it is short switching, the range is increased because earlier we were discussing about increasing the range by increasing L. Which,
Yes, sir.
yeah, now we are discussing increasing the range by decreasing C, so that energy storage is less. Right? Yeah. So that is done through gallium nitride or silicon carbide devices because their capacitance is low. So when they increase source switching range this way because their storage instead of here you are say here. Okay. So automatically your source switching range has improved basically. And when you enter into hard switching region, the storage is very low already. That switching losses will be less compared to silicon devices.
Okay, thank you.
If there are no further queries, sir, with your permission, could we conclude today's session?
Yes.
Thank you, sir, for the comprehensive outlook upon the various modulation techniques for the efficient system design through comparative analysis and the various aspects of switching design. Thank you, participants. A gentle reminder that there will be a session tomorrow as well, so do join in and further enhance the learning experience. Thank you.